Boundary conditions are what turn math equations into real physics. They are the difference between a result you can trust and one that just looks good. Welcome back to the OpenFoam guide. Today we are covering something that will show up in every CFD analysis you will ever do. Boundary conditions. And by the end of this talk, you will have a solid foundation that you can actually rely on. But first, what even is a boundary? Let's say you want to simulate a flow around a cylinder. You cannot simulate the entire universe. Nobody had that kind of computing power, so instead, you cut out a small piece of it, one that includes the region of interest. That piece is your domain. But the moment you make that cut, you create edges. And those edges need a definition. You have got the inlet where the flow comes in, the outlet where it leaves, and the cylinder itself, the object the flow moves around. Those are your boundaries. Now you have a domain, boundaries, and the equations to be solved there. But here is the thing, the math alone can't give you an answer. The equations that govern fluid flow, like the Navier-Stokes equations, are differential equations. That means they describe how things change, gradients, rates, relationship, but they have no idea where things start or stop. Think of it like this. If I tell you a car is accelerating at 5 meters per second square, can you tell me how fast it's going? No, because I haven't told you where it started. That's exactly the problem. So, to make our simulation actually solvable, we need to step in and tell the solver what's happening at the inlet, how fast is the flow coming in, what's happening at the outlet, what is the pressure there, for example, what's happening at the wall, is it moving, and so on. That is what boundary conditions do. Alright, now let's open our terminal and actually do this. But before this, I want to let you know something. Almost every boundary condition you will ever use comes down to just two fundamental types. Type 1, fixed value. You directly tell the solver what a variable value is at the boundary. For example, the velocity at the inlet is 10 meters per second. Type 2, fixed gradient. Here you tell the solver how a variable changes at a boundary. So instead giving the variable value itself, we are given the rate of change of it. For example, the temperature gradient at a wall is 0, meaning no heat flux through this wall. That's it. Two types, everything else builds on top of this. Okay, now we are ready to deal with OpenFoam. Taking flow around the cylinder as our example, creating the case structure, zero, constant, and system. And here, unlike other codes that bundle everything together, OpenFoam requires a separate file for every variable you are solving for. So you will need a file for pressure and another file for velocity. And if your simulation involves turbulence, you will also have input files for parameters like k, epsilon, omega, and whatever. Each of these field files is responsible for two critical things: setting the initial values inside your domain and defining your boundary conditions. Let's open the velocity file and write the input. Actually, almost nobody writes these files from scratch. It's much more convenient to copy files from the tutorial and adjust them to your case. But you still need to understand the anatomy of the file to make it work for your specific case. It starts with the header or basic information, followed by the foam file dictionary, where the file metadata takes place. Then you will see the dimensions. This is where you define the SI units for that variable. You load that the internal field. That's where you define the initial values for internal mesh cells. And finally, the part we are really here for, the boundary field dictionary. This is where you actually define your boundary conditions. Each entry in this dictionary corresponds to a specific patch or boundary in your mesh. For every patch, you write the boundary name, then you write the boundary conditions after the type here, this type keyword, and then followed by the value or any other parameters as needed. Okay, now first, we need to know what boundaries we have. I'm referring to the flow around the cylinder. Then we need to generate the computational mesh. For this, I'm using block mesh tool. I will delete this and write our input. Here in the boundary dictionary, we define our boundary. The first one we have, for example, is Inlet. And OpenFoam uses these names to connect image data to the boundary conditions in the field input file. So if the name in the mesh data doesn't match the name in the field input file, the solver will throw an error. Then each batch is assigned a base type, such as wall, batch, or empty. This is not a boundary condition itself. The base type simply describes the geometric nature of the boundary, so OpenFoam knows how to handle it. Finally, we write the faces that represent the boundary. For this case, we have inlet, outlet, cylinder, and the outer walls combined into one batch, since they will take the same boundary conditions. Same with the front and the back boundaries. We are in the wrong directory. And I also forget to include the control text file. It's required to be able to run the block mesh command. Now that the mesh exists, we go back to the velocity file and start assigning boundary conditions. For inlet, we will go with the fixed value condition, zero gradient for outlet, no slip for outer walls, no slip for cylinder surface, and finally, this is a two-dimensional case, so we will use empty to front and the back. And this is the workflow. You create the boundaries during meshing, You assign the boundary conditions in the field file. The patch name is what connects them. But let me be more precise about something. When I'm talking about to check patch names, I mean to check the boundary file inside constant polymesh. You should always check this file, especially if you are importing a mesh from an external tool. Salome, for example. Open the boundary file, verify names, check the base types, fix anything that doesn't look right. A name mismatch here or a wrong base type will break the solver. Now that we understand what boundary conditions are and how it's represented in OpenFoam, let's look at the most common ones in TFD and how to actually represent them here. Let's start by getting our workspace ready. I'll create a generic case so we can go through and explain each one. In this tab, I open the boundary file in constant polymesh. This is where you check your patch names and types to make sure that they match what you are about to assign. Next, open the field files, velocity and the pressure file. In another tab, I have a schematic of different physical boundaries. And beside this window, I'm showing you what boundary conditions look like inside the OpenFoam source code. Navigate to SRC, finite volume, fields, batch fields, and here you will find all of them. Now, before we go through any condition, it helps to know that OpenFoam organizes boundary conditions into three categories: basic, fundamental types like fixed value and zero gradient, constraint, conditions like empty and symmetry that define the geometry, derived, more advanced conditions built on top of the basic types. Let's see what exists in this file. Boundary conditions are required to close the problem, and their selection determines whether the equations can be solved numerically. That's good information to know. So you can take a moment and read through this. Alright, let's now walk through each physical boundary one by one, starting with the first, a simple inlet flow channel. As the inlet, we usually know how fast the fluid is entering our domain. So we prescribe the inlet velocity at this boundary, and fixed value is the type that does exactly that. And the inlet say we didn't know the pressure. We want the solver to compute it. So we use zero gradient for pressure. This lets the pressure adjust itself based on the velocity field throughout the channel. Okay, now let's move to the other tab and write these conditions in the field files. Before we write, let me share a habit that will save you a lot of time. Whenever you are about to use boundary conditions for the first time, go and open its header file. The header file tells you exactly what the condition does and how to use it in the field file in plain, direct language. This is the fastest way to get help, I guess. So let's do that. Here's the description of zero gradient. And here is how to use it. I'll copy it into the pressure file. For batch name, say we are assigning a boundary condition to this batch here, inlet. The same name must be used inside the pressure file. If you change it to lift, for example, use lift in the pressure file as well. But try to keep your names descriptive to make your case easy to understand for you and anyone else working on it later. And for the base type, it's called also boundary mesh type, must be compatible with the boundary condition you apply. Here, both fixed value and zero gradient expect something like patchy base type. For number of faces and start face, leave those unchanged. Now let's do the same for the fixed value condition. Read the description, and I'll copy this. Since the velocity is a vector field, we need to specify three components, x, y, and z. And with that, our inlet boundary is fully defined. Now let's move to the second physical boundary, the outlet. Here we flip the script completely. At the inlet, we know the velocity and solve it for the pressure. At the outlet, we know the pressure, say the flows charges to the atmosphere. So we solve for the velocity. And the boundary condition will be something like this. Outlet pressure, fixed value. Outlet velocity, zero gradient. This setup is often called the fully developed flow assumption. We are saying the flow is smooth and no longer changing as it leaves the domain. That is why zero gradient is used for velocity. But there is another option for outlet velocity that is good to know. And in many cases, it's actually the better choice. This condition is inlet outlet. Think of it as two conditions in one. It adapts based on what the flow is actually doing at the outlet. If the flow is leaving the domain, it behaves like zero gradient. But if the flow reverses and tries to come back in, it switches to fixed value condition. Let's see how we can apply this by opening its header file. Here is a description, and here is how to use it. The only required parameter is inlet value. This is the value that gets applied if reverse flow takes place. The value parameter is optional. It is just an initial value you get the field at the start of the simulation. And with that, the outlet boundary is fully defined. Now let's look at the third physical boundary we have, the wall. For wall velocity, we have two types. Type 1 slip condition. In this condition, viscous effects are ignored. The fluid is allowed to slide along the wall freely with no resistance. This is used when wall friction is not important to your simulation, assuming zero shear stress. Okay, let's see how to implement this. I'll copy it straight into the velocity file. For slip, the base type is patch. And for the pressure, it just takes zero gradient. This to ensure no mass is being pushed through the wall. Okay, the second type for wall velocity is no slip condition. In this case, we have a fluid that sticks to the wall. If the wall is stationary, the velocity at the wall is zero. This comes from viscosity. Friction between the fluid and the surface slowed the flow down to a complete stop at the wall. We use no slip condition when we are solving for viscous flow, boundary layer development, turbulence, and drag. In situations like biflow, flow over a car or aircraft, or heat exchangers. Now let's look at the no slip condition. Just replace slip with no slip. In fact, you can also use fixed value and set the value to zero. That will reflect exactly the same physics. And for the base type, you can use patch or wall. Wall type must be used if you are going to apply a wall function, since wall functions are only available when the base type is set to wall. Now let's talk about a different kind of boundary, one that doesn't represent a physical surface at all. It's more related to the geometry of your simulation. This is a symmetry boundary condition. This one simply makes sure that nothing can cross the plane of symmetry, but the flow can slide along it. It acts like a mirror plane. Symmetry boundary condition used in many situations. First, the far field. This is the region far away from any solid surface, far enough that wall effects and viscosity no longer influence the flow. Out there, the flow behaves like free stream, undisturbed, uniform, exactly like the incoming flow. Another example for symmetry, when the flow itself is symmetric. Take flow inside the pipe as an example. In this case, you don't need to simulate the whole pipe. Simulate half of it, and the center plane becomes your symmetry boundary, where you can apply the symmetry boundary condition. By doing this, you get less mesh cells, less computation time, but with the same physics, same results. That is actually a powerful trick, and almost all safety engineers use it to reduce cost without losing accuracy. Applying it is straightforward. Set the condition type to symmetry, and the base type to symmetry as well. That's it. Alright, I think that's a good place to end this video. But before that, I want to clear something up, and that is the empty condition. Empty is not a CFD boundary condition. It has nothing to do with the physics of your flow. It doesn't describe what the fluid is doing at the surface. It's simply a way of telling OpenFoam, don't solve in this direction. Think of it as a dimension switch. In our case, we have the front and the back set to empty. That tells OpenFoam this is a 2D simulation. Solving x and y ignores z direction. But what if you also set the top and the bottom to empty? Now you are down to one direction. You have just turned it a 2D simulation into a 1D simulation. So to keep it simple, front and the back empty, 2D simulation. Front, back, top, and bottom empty, 1D simulation. Do we have 0D? I guess we don't. Maybe I have to search. Anyway, now we are done. So see you in the next one.